So today we will finish off chapter 20. We'll talk about alpha beta unsaturated carbonyl compounds and how they react. And then we'll move into chapter 21. We've talked about aldehydes and ketones in chapter 20, but we're going to focus on them more specifically in chapter 21. And we'll start off with the typical introductory topics that we have at the beginning of a chapter covering a new class of compounds. But first, let's finish up a couple things with organometallic reagents from chapter 20. We've learned in 351M that epoxides can be opened by strong nucleophiles. And we know that our organometallic reagents are strong nucleophiles. So it shouldn't be a surprise that our organometallic reagents can open epoxides. And since they are strong nucleophiles, they would open an epoxide at the less substituted carbon. That would be an inversion process. The epoxide I've drawn for you on the board does not have a stereocenter, so you're not going to see the impact of that inversion in the structure of the product. But you would have an inversion ring opening, generating an alkoxide that then gets protonated by water, giving us an alcohol product. And the nice thing is we've opened the epoxide to form an alcohol while simultaneously forming a new carbon-carbon bond, making a longer chain alcohol from smaller building blocks. So that's the value of this reaction. One thing that's unique about this reaction is it is the one reaction where all three of our organometallics that we're learning about in this chapter will react in the same fashion. I've drawn it with an organolithium species here, with ethyl lithium, but we could use a Grignard reagent, and we could also use an organocuprate. This is the one reaction where the organocuprates behave in the same fashion as the Grignard reagents and the organolithiums. So all three of those organometallics will open epoxides at the less substituted carbon, generating alcohols. Any questions? Okay, so we've learned about carbonyl compounds. We know that carbonyl compounds are electrophilic on the carbonyl carbon. And previously, last semester, we learned about alkenes. We know that alkenes are nucleophilic. And then in chapter 16, we learned about conjugation. So let's put all three of those concepts together and consider what happens when we conjugate an alkene to an aldehyde or a ketone, or actually a carbonyl compound. It could be an aldehyde, a ketone, an ester. It doesn't matter. So we'll draw it in this fashion. Okay. So how does this react? Is it going to react like an electrophile? Is it going to react like a nucleophile? I've mentioned this previously, that clues to the reactivity of organic molecules can frequently be found in the minor contributors when we can have minor contributing resonance structures. So anytime we have a carbonyl compound, we have a minor contributor where we have a positive charge on the carbon and a negative charge on what was the carbonyl oxygen. Okay? And we've used this minor contributor to explain why carbonyl compounds are electrophilic on the carbonyl carbon. And these groups, these don't have to be methyl groups. These can be any combination of alkyl groups or hydrogens with these kind of empty valences I've put on this double bond. When we have an alkene conjugated to a carbonyl, we now end up with the ability to draw a second minor contributor because we have an allylic cation species in this minor contributor. So we can move the position of the double bond and we end up with a minor contributor that has a positive charge on the beta carbon. Remember, alpha, beta, we're just using Greek letters to count carbons as we go away from the carbonyl carbon. So this is our alpha carbon, this is our beta carbon. So we end up with a positive charge on the beta carbon in one of these minor contributors. So that tells us that these alpha beta unsaturated carbonyl compounds are going to be electrophilic at two different carbons, the carbonyl carbon and the beta carbon. We could also show this by drawing a hybrid structure. So our hybrid structure would have partial double bonds in this fashion, and then we would draw partial charges. And you would see in that hybrid structure that we have partial charges on two different carbons. Okay? So what this means is that there are two different locations that a nucleophile can attack an alpha beta unsaturated carbonyl compound. It's still going to be electrophilic, like all other types of carbonyl compounds, but there are two locations where our nucleophile can react. Okay? So we would have a strong nucleophile, and then we would follow that up by addition of water. And we could have the nucleophile attack at the carbonyl carbon in the same fashion as we were used to seeing earlier in this chapter. And that's referred to as a 1,2 addition process. Okay? That gives us an alcohol product. Or our nucleophile could attack the beta carbon, giving us a product that retains the carbonyl group, where our nucleophile is now attached to the beta carbon. And that's referred to as the 1,4 addition product. Okay? We use these terms, 1,2 addition and 1,4 addition, when we were talking about reactions of 1,3 dienes. This is a little bit different because in a 1,4 addition product of a 1,3 diene, we had the proton and the halide at the ends of the system. The proton is ending up here instead of here. So it's not exactly the same, but 1,4 addition, if you're referring to the oxygen as atom number 1, that's where our nucleophile attacks atom number 4. So that's one way to distinguish between these two products. Okay? So what do we get? Do we get 1,2 addition, 1,4 addition, or a mixture? Well, the results will depend on the nature of the organometallic species that we're using. Which type of organometallic reagent are we using in this reaction? Okay? So if we have, we're going to use this standard ketone here. If we have a Grignard reagent or an organomagnesium reagent, we're going to have the typical 1,2 addition that we've seen before, where our nucleophile attacks the carbonyl carbon, and then we add water in our second step to protonate the oxygen, giving us our alcohol. Okay? So organolithiums and organomagnesiums are going to react in the same way with alpha beta unsaturated aldehydes and ketones as they did with normal aldehydes and ketones. Okay? They'll just give alcohol products. Okay? So the difference will come with the organocuprate reagents. The organocuprate reagents are going to perform the 1,4 addition. Okay? So if we have okay, it's kind of a weird looking structure. It has a negative charge on the metal, but this is what our cuprate species looks like. We're going to have the electrons in the copper-carbon bond function as our nucleophile, and they're going to attack the beta carbon. And then what we're going to do is we're going to push the pi electrons from the alkene over here towards the carbonyl carbon, and then push the electrons in the carbonyl bond up onto that electronegative oxygen. And that's going to give us an intermediate looking like this. I'm just going to draw the CH3 out in this case so you can see this is the group we attach to our beta carbon. This is a resonance stabilized intermediate. It's called an enolate. It's something that we're going to learn more about in subsequent chapters, a very, very common type of intermediate. We've got two resonance structures that we can draw for that molecule, but the one with the negative charge on the oxygen is the major contributor. Okay. So now the way we're going to draw the next part of the reaction is going to be different than the way it's drawn in the book. The way it's drawn in the book is fine, but the way I'm going to draw it is going to be simpler. And you'll probably agree with me that if you have two mechanisms that explain a reaction equally well, the simpler one is going to be better. And so that's what we're going to use here. So we're going to add water. That water is going to protonate. So you might initially think, okay, we're going to protonate the negatively charged oxygen, and you could. But if you do that, you end up with an enol. And what happens to enols? We learned that in chapter 11, I believe it was. They tautomerize to give ketones. So then you have to draw a tautomerization mechanism, which is two steps. Why not just directly protonate at that carbon? We can do that by drawing the curved arrows in this fashion. And that gets us directly to the 1,4 addition product with the ketone. Okay? And then, of course, we'll have hydroxide as a byproduct. That's just going to form a salt with the lithium cation that we had from our cuprate reagent at the beginning. Okay? So this is the mechanism of 1,4 addition, which is also called conjugate addition sometimes. And we retain the carbonyl group in the product. We form a carbon-carbon bond to the beta carbon of our alpha-beta unsaturated carbonyl compound. Any questions about that? Yes, please. Why does it attack there? That is a great question. Unfortunately, there's not a great answer. The answer is complicated and related to principles that we're not going to learn in this class. And so it's not really related to steric hindrance. It's just related to different electronic properties of that cuprate reagent versus the Grignards and the organolithiums. That's as good of an answer as I can give you in this class. Sorry. All right, so we have a summary slide here summarizing what we've learned about our organometallics. They react with carbonyl groups, carbon dioxide, and epoxides. They can also react with alpha-beta unsaturated compounds. We've got a difference in reactivity between organolithiums and Grignards versus cuprates, except for our epoxide ring openings. There's a dichotomy when we're reacting them with either aldehydes or ketones versus carboxylic acid derivatives. With the former, we see addition. With the latter, we see substitution. But it's important to note that the substitution products can undergo additional reaction to give alcohols. Okay? So why are these reactions important? Well, two reasons. One, with our organometallics, we're forming carbon-carbon bonds, as I mentioned previously, making longer chain molecules from simpler precursors. And then also, in many cases, we're making alcohols. And alcohols are very useful molecules. We learned that last semester, a lot of different transformations of alcohol functional groups, dehydrations, oxidations, conversions to good leaving groups, followed by SN2 reactions. So it's important to know how to link the reactions from this chapter with reactions we've learned earlier in the class. And certainly there are synthesis homework problems that will help you with that. Okay? Any final questions on chapter 20. All right, let's shift to chapter 21, where we're going to go into more detail on aldehydes and ketones. And when we do have chapters focused on certain functional groups, we always start with our favorite topic of nomenclature. So, nomenclature of aldehydes is very similar to nomenclature of carboxylic acids. So that's going to make it easier for us to learn. First thing we're going to do is find the longest chain containing our aldehyde. And this is often how we write an aldehyde. It's a carbonyl group with a hydrogen attached, and we usually write it like that. We're going to drop the E from the parent name of that longest chain. We're going to add al. Okay, so that's good news. It's very simple. An aldehyde has al as its suffix. That should be pretty easy to remember. Okay. In the structure of an aldehyde, that carbonyl group is always going to be at one end of the chain. Okay, so the carbonyl carbon is going to be C1. So we don't have to associate a number. We know it's carbon 1, so we don't have to write it. So we don't have to associate a number with our carbonyl carbon of our aldehyde. However, we can have an aldehyde attached to a ring, coming off of a ring. Okay. So in that situation, the rules are a little different. We had the same thing with carboxylic acids. Okay. So if attached to the ring, then instead of adding al, we add carbaldehyde. Okay. And then the attachment point of that group is going to be C1 of the ring. So again, you don't need to include a number associated with that. Okay. So let's do an example of that, of a cyclic aldehyde, just to make sure we understand how this is done. Okay. And when you're drawing aldehydes, you don't always have to draw the hydrogen attached. Sometimes we do, other times we don't. It's optional. Okay. So what's our parent name and suffix for this molecule? How many carbons in our ring? 5. So what do we call it? Cyclopentane. What are we going to put on the end? Carbaldehyde. Cyclopentane carbaldehyde. We don't need a number, but we do have a prefix in front of that. What goes in front? 3-methyl. Okay, good. All right, so there are some common names with aldehydes. There are common aldehydes that were named prior to the creation of IUPAC nomenclature. And those names match with the names of the carboxylic acids. There was a table in chapter 19 that showed common names of carboxylic acids. And so instead of ic acid, you just have aldehyde at the end. So this would be propionic acid. It's propionaldehyde. This is valeric acid, valeraldehyde. And then you'll notice that we use Greek letters when we're using those common names. Where we talked about omega fatty acids. So you have the alpha carbon, the beta carbon. So this would be beta methyl valeraldehyde if you're using the common names. But then we see the IUPAC names, which you should recognize, not in parentheses. And recognize that when we're referring to a benzene ring as a substituent, we call it phenyl. Okay? So which common name should you be familiar with? There's just three that are important. We have our simplest aldehyde. What is this molecule called? That is formaldehyde. Okay. Our next simplest aldehyde, okay, it's a relative of acetic acid, so we would call it acetaldehyde. Okay, and then the third one, what do we call this? Benzoic acid is what it would be if it were an acid. So we're going to call it benzaldehyde. Benzaldehyde has a very strong cherry odor to it. Many aldehydes and ketones do have strong odors. Okay? All right, so what about ketones? How do we name ketones? It's also pretty straightforward. It's going to start out the same. We're going to find the longest chain containing our carbonyl carbon. We're going to drop the E and add -one. Okay. Again, a straightforward suffix. A ketone is going to have -one as its suffix. Okay, so that's pretty easy. There is a little difference here between aldehydes and ketones. Whereas the carbonyl group of an aldehyde is always going to be at one end of the chain, the aldehyde of a ketone is going to be embedded within the chain. So we have to use a number in this case to indicate where that ketone comes, where that carbonyl group comes in the chain. And so as you might imagine, based on your knowledge of IUPAC nomenclature at this point, we're going to number in the direction that gives the carbonyl group the lowest number. Okay. So let's do a simple example. What's our parent name? Okay, pentane. What's our suffix going to be? Okay, pentanone. And this is one of those cases where IUPAC, since they were sitting around with nothing better to do, they decided to change the system. And in the book, they have the new system where you stick the number in the middle, right in front of the suffix, but that makes it more awkward to say. And so I stick to the old system personally, where the number is going to go in front of the parent name. Okay? So either way is correct, and I'm confident, based on your results on the last exam and how well I know you, I'm confident that you are smart enough to know that both of those names would be equivalent and that that's not going to trip you up. So what number are we going to put in front of the pentanone? We're going to put a 2. Okay. And then what's going to go in front of that name? 3-methyl. Good. 3-methyl-2-pentanone. Okay. Now for naming cyclic ketones, it's different from aldehydes because the ketone carbonyl is often part of the ring. Okay, so we don't have, for aldehydes, we stuck on that carbaldehyde. That carb is referring to this extra carbon that's outside the ring that's not accounted for when we say cyclopentane. But if we have a ketone as part of a ring, we don't need to do that. We don't need a special suffix. And so we can just call it a cycloalkanone, depending on how many carbons there are in the ring. Okay. And as you would probably guess, we're going to set The carbonyl carbon is carbon 1, so we don't need a number in the case of a cyclic ketone. Okay? So what's the parent name plus suffix of this molecule? Cyclohexanone, exactly. This will be cyclohexanone. And we don't need a number in front of that because we know that the carbonyl carbon will be carbon 1, cyclohexanone. Okay, but what are we going to put in front? Okay, so we can put 3-isopropyl. And then what else? 4-methyl, okay. So remember, we treat prefixes differently in IUPAC nomenclature based on whether they're italicized or not. Isopropyl is not italicized, so that starts with I. Methyl starts with M, so we've ordered these correctly, okay? Any questions about our ketone nomenclature? Yes? That's a good question. Probably because that's the first carbon where you could have another substituent, right? Because if it's an aldehyde, you've got a hydrogen over there on one side, and so the first place you could have a substituent would be the alpha carbon. So that's probably why, and it's the same way with carboxylic acid. So that's probably why that started. I don't know that for a fact, but I suspect that's why it started that way. Other questions? Yes, Trent.
Kind of going off of that, then do you just call the carbonyl carbon, or is there some special?
Yeah, you would just say the carbonyl carbon, especially if it's an aldehyde or a ketone, you'd call it a carbonyl. If it's a carboxylic acid or an ester, you might call it an acyl group or a carboxylate or something. But we'll just call them carbonyl carbons if they're aldehydes or ketones. There is, I'm sure you'll love this, there is another nomenclature system for ketones. This is a common name nomenclature system. And it works for simple ketones where the two alkyl groups that are attached to the carbonyl group are small alkyl groups that we can name. We had this same system for ethers back in 351M, where we would name the two alkyl groups and we would put ether at the end. Okay? So if we use that pattern, that simple naming pattern for ketones, we would name the two alkyl groups in alphabetical order and then put ketone at the end. So let's try that here. What's our first alkyl group in this molecule? Sec-butyl, very good. Very proficient with the IUPAC alphabet. Sec-butyl starts with B. This is a sec-butyl group. And then what's our other alkyl group? Methyl. So we have sec-butyl methyl ketone. So either of these names is valid for this molecule. One is IUPAC, one is common. Both of those names are valid. There are some common names, acceptable common names for ketones. There's 3 that we will learn. One you're familiar with if you're taking the lab, and we've seen it in class before. What is this ketone? You use it all the time in the lab to rinse your glassware. That's acetone. Okay, it's a polar organic solvent that dissolves a range of molecules, so it's very good at dissolving residues in your glassware. So every organic chemistry lab in the world uses acetone to rinse out the glassware. Okay. This molecule is called acetophenone. So it's similar to acetone, but we have a phenyl group attached instead of a methyl group on one of the sides. So it starts out like acetone, but then you put phen in the name to indicate the phenyl group. Okay, so that's acetophenone. And then if we have 2 different ketones or 2 different benzene rings, then we call that benzophenone. Okay. And then acetophenone can be used as kind of a base name or a parent name in the same way that phenol and toluene can be used. And so if we had a substituent, another substituent coming off of our acetophenone, we can name that as an acetophenone derivative. What would we put in front of this name? Okay, bromo. And what would go in front of the bromo? Yeah, this is metabromo. Metabromo acetophenone. Okay? So lots of good nomenclature. Sometimes we refer to aldehydes and ketones as substituents. Maybe they're coming off of a ring or a long chain of some sort, and we call them acyl groups. We've already seen that term. We talked about fruitocrase acylation, so you already are familiar with what acyl groups are. And there's 3 acyl groups that have common names that you'll see frequently. Okay. This is known as the formyl group, right, related to formaldehyde. So that so if this is attached, hanging off of a ring or a chain, you could say that's a formyl group. You'd name the molecule like this. You typically wouldn't use formyl in the name, but you could refer to this as the formyl group that is attached to that particular molecule. Okay. And this is referred to as an acetyl group. Okay. And then this particular acyl group is referred to as a benzoyl group. Okay. So some common names when we're just referring to the groups. Okay. All right, and then we have one final component of nomenclature to discuss, and that is, what do we do if we have a molecule that has a carbonyl that's an aldehyde or a ketone and has an alkene present? We've seen those. Those are our alpha beta unsaturated molecules. Those are up here on the top board now. How do we name them? What gets priority? Does the aldehyde or ketone get priority, or does the alkene get priority? And the answer is the carbonyl group does. Okay, so we would name it as an enone. Okay, so here's an example. We're going to have 2 suffixes, one for the alkene and one for the ketone. So this particular molecule with 5 carbons, we're going to call it pentenone. The higher priority functional group goes last in terms of the suffix. Here we're going to need 2 numbers, one to pair with each of our suffixes. So we are going to need to put a suffix or put a number in this spot right here. So what number is going to go here? Okay, I think I heard 2. That's correct. Because the ketone gets priority, you're going to number the chain from the direction that gives the lower number to the ketone. And then what number is going to go in front of our pentene? 3, so that's the one referring to the alkene. The book's going to stick that in the middle here. I prefer to put it here, but you could do that. And then what's going to be our prefix in front of that number? 4-methyl, yes, okay. So when we have an alkene, it doesn't have to be conjugated. This one's conjugated, but any molecule that had both an alkene and a carbonyl, you would call it either an enone or you could call it an enal. Okay. Any final questions on nomenclature? All right, let's move on. Let's talk about the physical properties of aldehydes and ketones. Can aldehydes and ketones hydrogen bond to each other? No, they cannot. They do not have a hydrogen attached to the oxygen. Can they hydrogen bond to water molecules? Yes, they can hydrogen bond to water molecules. So we would expect carbonyl compounds to have boiling points lower than alcohols, because alcohols can hydrogen bond to each other. But we would expect them to have water solubility similar to that of alcohols, because they can hydrogen bond to water molecules. And so this table here summarizes that and shows us exactly that that's exactly the case. Here we have an aldehyde and a ketone. We have their boiling points listed. You can see that that's significantly higher than an alkene of similar size and shape, significantly lower than an alcohol of similar size and shape. And we see water solubility. As long as we have 5 carbons or less in our aldehyde or ketone, we have pretty significant water solubility. Okay. All right, let's talk about spectroscopy. So here's an IR spectrum of an aldehyde. And the dominating feature is this carbonyl group. There's a typo here. These should be switched. Right? The sp2CH stretch is the one that's above 3,000. The sp3CH stretches are the one below. So please recognize that this is these two groups should be switched on this figure. But the main thing we're looking at is our carbon-oxygen double bond stretch. That's at around 1,700. Usually it's about 1,730 for aldehydes, about 1,715 for ketones. Your book tells you a couple of things about the carbonyl stretches in ketones. It says that for cyclic ketones, the more ring strain you have, the higher the number is. There's not really a great explanation for that, so we're not going to focus on that aspect. But there is something that we need to focus on about the stretches, the CO stretches in ketones. And that is what happens when that carbonyl group is conjugated. Okay, so here, this is acetophenone. We have the carbonyl group conjugated to a benzene ring. This is 2-cyclohexenone. We have that ketone conjugated to an alkene. And it turns out that in both cases, the wave number value for the CO stretch is a bit lower than it is in most carbonyl compounds. And this is general. Whenever you have a carbonyl group conjugated to a benzene ring or to an alkene, you're going to have a slightly lower value. Now, if we go back to Hooke's law, we learned that back in chapter 13. Hooke's law is the law that underlies the position of the various stretches in the IR spectrum. Are stronger bonds going to require more energy or less energy to stretch? More energy, okay? And more energy correlates with a higher wave number. Wave number is directly proportional to energy. So these lower values for the wave number, the stretching frequency of conjugated carbonyls, indicates that those carbonyls are actually weaker bonds than the unconjugated carbonyls. Why is that? While you're thinking about it, I'm going to draw some structures on the board for you that might help you understand, okay? So here's a simple conjugated ketone. We have a minor contributor that we can draw, looking like this. And we learned this earlier in class today. We have a second minor contributor when it's an alpha beta unsaturated ketone, looking like this. All right. So with these structures drawn on the board, do we have an explanation for why the conjugated aldehydes and ketones will stretch at a lower frequency than unconjugated aldehydes and ketones? Any answers? All right, I'll draw something else. Let's draw the hybrid structure. Okay, here's our hybrid structure. What's our carbon-oxygen bond order in this hybrid structure? Is it a whole number? Is it between two whole numbers? What's it between? The bond order of this carbon-oxygen bond? between 1 and 2, right? Is it closer to a double bond or a single bond? It's closer to a double bond because the major contributor has a double bond, right? But whereas most aldehydes and ketones have one minor contributor with a single bond, alpha, beta, and saturated aldehydes and ketones have two minor contributors with single bonds. So the bond order of a conjugated aldehyde or ketone is slightly lower than the bond order of an unconjugated aldehyde or ketone. Let's just throw out some numbers. Let's say that in a, just to randomly make up numbers, not randomly, but we don't know the exact values. Let's say that a normal aldehyde or ketone has a bond order of 1.9, then our conjugated one would be like 1.8 or 1.7. So we have a slightly lower bond order, slightly weaker bond, and that's reflected in this lower stretching frequency. Okay? Questions? All right, let's look at NMR spectroscopy. NMR spectroscopy, the key feature is this highly de-shielded hydrogen due to the circulating pi electrons of that carbonyl group and the electronegativity of the oxygen. So that shows up between 9 and 10. It's the only type of hydrogen that shows up between 9 and 10, so it's very easy to spot. There is splitting, right? We have neighboring hydrogens here, so this is split into a triplet. In the C13, that carbonyl shows up around 200, highly de-shielded. Okay? Any questions? All right, interesting aldehydes. Our simplest aldehyde, formaldehyde. What's it used for? Preserving biological specimens, right? It also can be used to make polymers. The world's first synthetic plastic, known as Bakelite, is created by a reaction between phenol and formaldehyde. It's a relative of the Friedel-Crafts reaction. And you get reactions at ortho, meta, and para positions if your concentration is high. And you get this very rigid plastic material. And then finally, many aldehydes and ketones have very interesting odors. Here's a figure showing some of them. And some of these are pleasant odors. Some of them are viewed as not so pleasant. But many aldehydes and ketones are quite fragrant. So we'll stop there. And we'll learn about how to prepare aldehydes and ketones as well as some of their reactions on Monday.